Okay, welcome everyone, good afternoon, and welcome to this special flagship lecture of the ICTS, the ICTS Infosys Chandrasekhar lecture series, the first of which is usually at a colloquium level, meant for a broader audience, and followed by two more technical lectures. This is one of the special lecture series that we have for having with very distinguished scientists in the physical sciences giving these talks, and there's a long history of various people, and you can see some of the excellent lectures on our webpage for past speakers. There's a similar one, Ramanujan series in the mathematical sciences, and the Turing series in the biological and engineering, computer science. And all of these have been generously supported by the Infosys Foundation. So I like to acknowledge that support. It's a special pleasure to have Joel Moore from Berkeley give this installment of the Chandrasekhar lectures. Of course, as all of you know Joel, and we'll hear a scientific introduction soon from Subrata. But Joel is I personally find it very nice to have him here for this occasion, because he has been an old friend of India. His first visit was nearly 30 years ago, and he has been multiple times to ICTS and been a very strong support for ICTS's growth in areas of condensed matter, StatMech, etc. So I'd really like to thank you for taking the trouble to come all the way here over the Thanksgiving weekend, I guess, in the US. So now I'll just hand it over to Subrata to give you a scientific introduction to Joel and get on with the talk.
Thanks a lot, Rajesh. It's my great pleasure to introduce Joel Moore. Joel received his bachelor's degree in physics, summa cum laude, from Princeton University in 1995. And then he spent a year as a Fulbright scholar, a part of it actually in TIFR Bombay, before going to MIT, from where he obtained his PhD in physics. He then spent a year at Bell Labs before joining the physics faculty at the University of California at Berkeley, where he's currently a professor. Joel is an extremely decorated scientist. He is an elected member of the National Academy of Sciences, a Simons Investigator, an elected fellow of the American Physical Society, and a Chern-Simons professor. He also has an additional appointment as a senior faculty scientist at the Lawrence Berkeley National Lab. So, as you all know, Joel is one of the leaders in the field of theoretical condensed matter physics. And while he's probably best known as one of the discoverers of the 3D topological insulator, he has made seminal contributions to a wide variety of topics in condensed matter physics. So his work has been very important in furthering our understanding of topological phases of matter and the properties of topological materials. Joel has also contributed extensively to the study of the dynamics of quantum systems. In this area, his work has spanned the entire range, from employing sophisticated numerical methods to developing an analytical understanding in terms of effective hydrodynamics. So a recurring theme of his research has been the use of entanglement to analyze problems in condensed matter physics. And this, of course, has extended our understanding of quantum correlations in many body systems, and also established connections between the fields of condensed matter physics and quantum information, which, as you know, is one of the themes of this meeting. And Joel is going to talk about all of these things during the course of his lectures. On a personal note, I should say that Joel was my postdoctoral mentor. And in addition to being an exemplary scientist, he's also an exemplary mentor. It's my very great pleasure to welcome Joel and invite him to give the Chandrasekhar lecture.
Before that, a small little ceremony where we just, a small memento on behalf of ICTS. It's a sweatshirt, has your poster of your lectures, and a mug of ICTS. So
all very useful, thank you.
Yeah, okay, so looking forward to it.
All right, I feel very honored to be a Chandrasekhar lecturer. As you heard, I've been coming to India for physics ever since I was just about to start graduate school. I've certainly gained a lot more from Indian physics than it has ever gained from me, but I'm very, anyway, I feel very happy to be here. Now, one caveat is that this lecture doesn't have that much to do with the central topic of the discussion section we're having, because I figured since I only get to be Chandrasekhar lecturer once, I should probably talk about what I've spent a large part of my career doing, which is these topological materials. But you will see, if you happen to stick around for lectures 2 and 3, things that are more about quantum information and this new era that we're in. We are sort of in a new era of topological materials, but it's not that new. It's been going on for a while. I will try to tell you 1 or 2 new things. The main new result I want to build up to is how some new topological materials let us see the first quantized nonlinear effect of a certain kind that I'll tell you about. But maybe the big goal is to try to show you that many objects that are invented in one area of theoretical physics, if they're sufficiently beautiful, will appear in another area of theoretical physics. So I'll try to tell you about some pictures and objects over the last almost 40 years that have been surprisingly helpful to understand materials. And I'll try to give a bit more background as I go along. So as a big motivation for why we do condensed matter physics, aside from applications, which tend to get a lot of focus, we live in a very remarkable world. It has a lot of fundamental particles that we understand, and some things like dark matter that maybe we don't. But the traditional way to find new particles was to break apart matter into smaller and smaller pieces using larger and larger machines. And these pieces include bosons and fermions. They include particles and force carriers that mediate forces between massive particles, say. But they don't include everything. There are new particles that get made in condensed matter and new responses. And that's a large part of what drew me to the field. So in this talk, what I'll mostly be talking about are materials where the particle's the electron, but some unexpected kind of response happens. Often dependent on a gauge theory, like the kind you study in high energy physics. But a more general reason for doing what we do is, it could be a new kind of response that emerges, or it could be a quasi-particle or something like that, or it could be a new sort of fluid. And all of these will appear at various points during my course of lecture. But basically, even though we start from nuclei and electrons and electromagnetism, what comes out can be very simple again, but unexpectedly different from the parts I started with. So the outline of this talk, this is the one that's meant to be a little bit pedagogical and actually teach you something. So I'll teach you something that I think should be part of the standard graduate education for pretty much anyone in theoretical physics these days, which is how do certain properties of electrons and solids teach you a new way to look at gauge fields, and how does that give you surprising electromagnetic responses that we continue to discover. So the newest one I'll talk about is just in the last few years. It's a kind of chiral photocurrent. And that was enabled by the discovery of a new family of materials that were first proposed in the 1930s, well before topological insulators and things like that. There was the idea of, they weren't called topological then, but certain kinds of semimetals. And the main new stuff I'll talk about was motivated by trying to understand, once you have Dirac or Weyl semimetals, what do they do? What is some trick that they do that ordinary metals or insulators or semimetals don't? And that was a fun path to go down. And maybe it let us understand that some of the mathematical objects and pictures that were originally developed to understand quantized phenomena like the Hall effect in insulators also appear in metals, but with interesting differences. And in fact, even in far from equilibrium, high frequency properties. So if you like, the general takeaway, the pedagogical aspect is basically to teach you that some fairly simple objects, mathematical or geometrical objects, turn out to be very useful for the physics of solids, not just at equilibrium, but even far away from equilibrium, not just for transport, but even for optical properties. And I believe that these geometrical objects are actually quite natural in any sort of quantum problem. So they actually appear a little bit, or related versions appear in questions like entanglement and so on. But maybe the physics question will be the first examples of quantization in metals and how is it different from insulators. But actually, just to kind of convince you that I'm not crazy and that some level of quantization is possible in semimetals without getting into fancy things, let me tell you a neat experiment as kind of motivation. But first, in case you're wondering, lectures 2 and 3 will be about, well, lecture 2, more correlated materials and how quantum computers are starting to make a contribution to a physics problem I actually cared about anyway. So far, quantum computers have mostly been used to solve physics problems like boson sampling that we didn't really have a reason to care about before quantum computers, but that's starting to change. And then the last part will be about how quantum information is changing the way we look at many-body physics and how that's been happening over about 20 years. So the warm-up, an experiment you can do with your hands, I think it's the simplest way to measure the fine structure constant of the universe, at least if you have a friend who can give you a sheet of graphene. If you get graphene and hold it up to the light, you can mostly see through it. It blocks about 2.3% of the light in the visible. And that 2.3% is actually a special number. It's pi times 1 over 137. So you all know pi, and I think most of you know 1 over 137, that's the fine structure constant. It's probably the most important dimensionless number for why the universe is the way it is, at least the things we run into most of the time. And that is not very topological, and I'll actually mention later that I think it's kind of a cosmic accident that this experiment works so well. Basically, there's an interaction correction that you would expect to be large, and instead it's more at like the 1% level. But it just shows that because this is a semimetal, graphene, you've probably heard, is a single layer of carbon atoms. It has a very special energy-momentum relation, like a relativistic electron, but the velocity is not the speed of light. It's about 300 times smaller. But that artificial velocity drops out, and what you measure is the real fine structure constant with the velocity of light in vacuum. So that tells you that maybe quantization is not just limited to insulators. Maybe you can find things that, it's not quantized to 1 part in a billion like the quantum Hall effect in insulators, but you can find something that is pretty well quantized. At least the natural scale for the effect is just the fine structure constant and a numerical factor, which is just pi. So are there other examples like that where maybe it's a little bit deeper, maybe it happens for some topological reason? And since I keep using that word topological, let me start off in a second with sort of definitions of all that. So first of all, the main experiment I'll build up to, so this is going to involve maybe 20 years of work that I've done in this area, but the main newish results, here are the theorists who are involved, who all passed through Berkeley and have now moved around the world to Spain, France, Japan, San Diego. And these are the experimental collaborators who managed to see the effect. Let me start off with what made me want to be a condensed matter physicist and how there are now 2 different notions maybe of universality and how topological universality is in some ways even simpler or more straightforward than the most famous kind, which is universality at phase transitions. So very briefly, something that will appear a lot in this talk is symmetry. If you think of a crystal, it has a lot of symmetries like rotations and translations, but it has fewer than the vacuum, because the vacuum you can translate or rotate by continuous amounts, and the crystal only has discrete symmetries, and we can classify crystals by what symmetries of the vacuum got broken. And it turns out that until the advent of topological phases, most of the phases that we ran into, the kinds of order, we could classify in terms of those broken symmetries. An example that's relevant to topological insulators and things like that, we think of magnets, like a ferromagnet, as picking out a direction of spin. The electron spins point in one direction, but they also break time reversal symmetry. You could tell from the equations of motion that of a particle in a magnet, say, that something has changed between t and minus t. So the universality aspect is this famous old result from the 70s, but this is what I found so amazing that it made me want to learn statistical physics. If you go and look at simple fluid like water and forget about ice, which is kind of complicated, then there's a liquid-gas transition, boiling. But if you go up to high enough pressure and temperature, that transition disappears. The way that transition disappears, you could measure it by the density difference between liquid and gas, and that goes to 0 like some power. You could take a different system that is very quantum mechanical, the electrons, say, in a bar of iron, which below some temperature becomes a ferromagnet. If you were to measure, in an ideal magnet at least, the strength of the spontaneous magnetism and how that disappears at the Curie temperature of about 1,000 Kelvin, you would realize that the spontaneous magnetization disappears like a power law. And the remarkable fact is that even though this is a quantum system of electrons and this is a classical system of atoms, and this very clearly has some kind of symmetry in the phase diagram and this does not, that number beta is the same. It's like our physics version of pi or e. We don't know how to calculate this number exactly, but people doing conformal bootstrap have added some decimal places to theory since I made this slide, actually. But it's sort of remarkable that close enough to the phase transition, all the microscopic differences between these two systems are irrelevant. But an even simpler form of universality, so this was a great success of physics in the 70s, won a Nobel Prize for Ken Wilson. A great success of experiment, later understood by theory, was the quantum Hall effect as an example of macroscopic quantization from topology. So very briefly, one of the first experiments you do when you get a new semiconductor, say, is you put a magnetic field on it and you run current perpendicular to the magnetic field and you measure how much voltage builds up because the charge carriers got bent by the magnetic field. And that lets you tell, for one thing, if you've got electrons or holes. And normally, at weak magnetic fields or in a three-dimensional material, you see a straight line in the so-called Hall resistivity. However, if you go to larger magnetic fields in a two-dimensional electron system, and it doesn't even have to be a super clean electron system, you see that there are flat regions where rho xy is constant and basically equal to h over ne squared. Or if I convert it to a conductivity, the Hall conductivity on one of these plateaus is an integer times e squared over h. That's just the bare electron charge squared and Planck's constant to about 1 part in a billion. And the excitement is that's happening in a big chunk of material. It certainly has a lot of defects. It has thermal fluctuations and so on. And yet some combination of quantum mechanics and topology gives you this very macroscopic protection. In fact, this was recently used as part of redefining the system of units a couple years ago. So far, I don't know another great application of the quantum Hall effect. The fractional quantum Hall effect may lead us to a topological quantum computer, but at least the integer Hall effect, it's an example where you don't have to measure one electron. You can measure e squared over h with this measurement. There's a neat measurement with superconductors that is also in hindsight kind of topological and measures e over h, and that means from two macroscopic measurements on solids, you get E and you get H without ever having to pull out one electron. And of course, there are fractional states here with fractional particles, and to hear about those, you will have to show up for lecture number 2. So very briefly, what happens in the Hall effect? So the original Hall effect was discovered by Hall, not surprisingly, back around 1890, and it wasn't quantized. So what makes it, what changes when you add topology? And maybe a general lesson is that symmetry tells us whether some material or some complicated system allows a response. And there's a principle that if the response is allowed, then it should be non-zero. There's no reason for it to be fine-tuned to 0. This is one of Landau's kind of principles. But what topology does is often fix a magnitude to be some special values. 0 is one possibility, but you also get things like e squared over h in that Hall example. So I'm going to be talking, when I come to recent experiments in the second half of the talk, I'll be talking mostly about optics, because it turns out that topology explains some puzzles about optics in solids, but maybe some symmetries to keep in mind. In general, a nice thing about crystals is that when you go into a crystal, you can change the symmetries of your world. You might see that inversion is breaking. That happens in gallium arsenide, for example. And that's enough to allow second harmonic generation along some directions, which just means if you're putting in light at frequency omega, then you'll see some light coming out at frequency 2 omega. If you want to make a solar cell or something like that, where current comes out from unpolarized light with a particular direction, that's a polar material, like one with a particular axis. So polar is a subset of inversion breaking. And then a different subset of inversion breaking would be chiral materials, which you could think of as having a screw-like structure in 3D. But the surprise is that topology, can quantize a magnitude, and it's also, I think it's fair to say, it's forced us to think a little bit more carefully about symmetry over the last few years. So now we come to I want to say a little bit about what a Berry phase is and what a Berry phase gauge field is and so on, and how we actually compute them, which is more like a Hunter-Rotnam phase. But just to kind of indicate why this is a useful concept. So pedagogy means I'm supposed to try to teach you something, at least as I understand the root of the world. So I'll teach you that there are abelian gauge fields and even non-abelian gauge fields in many crystals that matter. And it's the same mathematical structure in a way as in particle physics, but in other ways it's kind of different. So we're going to write down some geometrical gauge objects inside a crystal, and I'll define these fields A and F before. And the good news is, if you remember your electromagnetism, you're most of the way there. And what these have been good for, so maybe the first use of these was to understand some topological phases, then topological phases when you add a symmetry condition. So topological insulators are basically a topological phase that exists because you required time reversal symmetry. They have also turned out that some physical quantities that you might care about in a solid, even if they're not really quantized, we didn't really understand them till Berry phase. And the simplest example is the electrical polarization of a crystal. That's just saying, if you have a crystal, does it have an electrical moment that points in some direction? People thought about how to calculate that for about 50 years, and then it was explained by Thouless and Vanderbilt and people like that, that it was an example of a Berry phase quantity. An example I'll talk about, because it's the first non-abelian Berry phase effect in solids, is the magnetoelectric effect. And then the recent area is maybe realizing that even when you go to metals and even when you go to dynamical properties, so there's some kind of semi-classical versions in these papers, and then the new thing will be the quantized version. These same geometrical objects still turn out to be useful. And then there are new geometrical objects that I only mention at the very end, because those may be more, that's more of the technical side at this point, but I think there's still exciting stuff going on. And since this is meant to be a little bit pedagogical, if you'd like to interrupt, I won't be offended at all. In fact, it will probably help me get to 90 minutes. So feel free to ask me some detail. So basically, there's going to be a kind of curvature of electronic states in a solid, and that will underlie the quantum Hall effect. In fact, integrals of a curvature, you might have heard, can be sort of quantized in our language, like the total curvature of a sphere. So what I want to start thinking about is just the adiabatic theorem in quantum mechanics, and how the adiabatic theorem is only kind of half of the truth. So the true fact is that if you have a non-degenerate state of a Hamiltonian, and you change the Hamiltonian slowly in time, you will stay in that state to good accuracy. However, the system can build up a phase that is actually observable if you could interfere, say, one copy of the system that was changed adiabatically and one copy that wasn't. And we write that like we use the symbol of a vector potential that lives in parameter space. And for us, the parameter space is going to be momentum space. So something about how the wave functions change as a function of parameter, I'm going to claim gives rise to physical objects. If I want to phase, then I can integrate this around a closed loop. So I'm going to say a bit more about this object and what it means to say it's a gauge-like object. But for the moment, just think about, I've got a non-degenerate state at each value of the parameter. And as the wave function changes, I could make this inner product between the wave function and the derivative of the wave function, and maybe that object will make some mathematical sense. So I'll come back to the question of why do we write it this way, and what about the fact that the overall phase of these wave functions is somewhat arbitrary. But first, especially since I'm in Bangalore, I wanted to mention that Berry, I think, Berry's very honest about this in his paper. Berry didn't really invent the Berry phase. Berry showed that people in different areas of science had stumbled across the same structure, and he really explained that these were all the same things, and sort of the continuous version that I wrote down on the previous slide. But the first example in a physical problem of this kind of geometrical phase was worked out by Pancharatnam over at the Raman Research Institute. He was not only Raman's student, I believe he was also Raman's nephew. So you can imagine that that might be challenging on some level, but he got some good work done. Tragically, he passed away quite young, so he didn't get really to follow up on his great ideas. But if I were to think about the Berry phase and actually trying to evaluate this integral, well, I would probably discretize it, because if we're doing a material or something, we can't solve it at every point. And then these inner products, there's a nice way to write them in terms of the projection operator onto the adiabatic state at every point. So we often wind up working on a grid. We can't really take n to infinity and get the continuum Berry phase. And what Panchratnam was really thinking about was effectively projection operators arising in like a 3-point example in optics. And actually, in a lot of our modern work, including the new geometrical objects I'll talk about at the end, it's actually much nicer for other reasons to work with these projection type operators than to work with wave functions, because wave functions have a gauge, and it's true that at the end of the day you get gauge invariance. You should, or else you made a mistake, and I'll define that gauge sense in a second. But if you work with the projection operator, you could see that if I change this wave function by e to the I theta, it picks up an e to the minus I theta from this half of the projection operator. So overall, this object is explicitly gauge invariant. And it's nice to work with explicitly gauge invariant objects. It means that everything you're writing with is uniquely defined. All right, so the gauge freedom, on the other hand, we don't know how to make everything gauge invariant with projection operators. And it's also true that writing things in this gauge dependent way has been extremely useful to port over ideas from high energy physics and field theory. But the basic idea of this Berry phase, one way to tell that this does make some physical sense, suppose I chose one phase convention and you chose another, so that the phase, let me just assume that it was a continuous function of the parameter for now. Then if I make this change, the Berry connection, this object A, it changes by a gradient of that phase factor. And you probably remember that's just like the vector potential in electrodynamics, but that's a clue that we know how to make physical objects in electromagnetism. I just don't work with A itself, because that's gauge dependent. I work with things like curl of A or loop integrals of A. And the easy way that this all generalizes to non-abelian gauge fields is just, suppose I had more than one degenerate state, or sometimes in a crystal, the occupied states aren't degenerate, but it doesn't matter because they're all occupied. Then I would just add sort of indices within that degenerate state space. And now A becomes a matrix. And instead of having a U1 gauge invariance, it has a UN gauge invariance. So just by thinking about any quantum mechanical system with parameters, an adiabatic evolution, you're naturally led to a U1 gauge field for non-degenerate states and a UN gauge field if multiple states come together. So is this just playing around, or does this F mean something? Well, since we give it a name, it probably means something. And this is what at least a part, probably about half of what Thouless won the Nobel Prize for in 2016, which was, he wasn't the first one to explain that integer Hall effect. That's something that Laughlin did using a very unconventional picture called Laughlin pumping of how electrons move. But what Thouless did was the puzzle of, suppose I didn't want to be clever and think about a new kind of transport. I just want to understand in a crystal what tells me what crystals would have the quantum Hall effect, and how can I get to that using ordinary sort of Kubo formula calculations of transport. And when you do that, what you find is quite remarkable. You get this expression for the quantum Hall effect of a two-dimensional crystal is some integer times e squared over h if the chemical potential is in a gap between bands. And that integer is the sum over occupied bands of some integral, but this integral is over the two-dimensional Brillouin zone. And what appears in the integral is just the Berry curvature. So this thing inside the parentheses is that F. So the closest analogy for this I know is the total curvature, total Gaussian curvature of a closed two-dimensional surface is quantized and just gives you the Euler characteristic. 2 minus, twice the number of holes, something like that. So here, this is saying that the total winding, in a sense, of the wave functions in any two-dimensional crystal for every band is an integer, and I add up all the bands and I get some number. So that was maybe the first use of this F and A to get an observable quantity. Now we have a big list. So the same list I showed before, but let me dive right in and try to give sort of other examples beyond the quantum Hall effect. So that Thouless paper, TKNN, Thouless, Komodo, Denice, and Nightingale, is an example of something that was kind of a undiscovered classic, or people knew it was very beautiful, but they already sort of understood the integer quantum Hall effect, and it wasn't exactly clear what these mathematical objects would be good for quite a long time. And then people started understanding that there are other kinds of topological phases that you can get out of those objects, which were these topological insulators and so on. So since even these are now fairly old, like I said, I'm mostly going to talk about metals, but I will try to give you a quick picture of the magnetoelectric effect, because I do, I do find it very neat how different things in physics, in this case the Axion, sorry about that. So the magnetoelectric effect is a neat example of how things in different areas of physics can come together. All right, so what I want to claim is that, in a sense, particle physicists in the 1980s figured out the right theory of the 3D topological insulator. Not really, because they didn't have the microscopics or the solid state motivation or like how to figure out if a material is in that category. But there was a very prescient paper by Wilczek in 1987, and I want to explain how this so-called Axion electrodynamics, which he was thinking about, because if we have this particle called the Axion field will couple to the ordinary electromagnetic fields this way. Just thinking about symmetries on this term leads you to a conclusion that there might be not one kind of time reversal invariant insulator, but two. And that turned out to be true many years later. So the basic idea of what Wilczek was thinking about was, if I think about this coupling, E dot B is a little bit special compared to E cross B or other bilinears I could make. It is a total derivative, for one thing, of ADA. And there's kind of an argument that you'll be familiar if you've seen it in particle physics, that the coefficient in front, if I'm dealing in a system with no boundaries, the coefficient in front should really be thought of as an angle. So I'll tell you what that means in condensed matter language in a second, but for a moment, take that as an article of faith. So theta is an angle, which means it's defined modulo 2 pi. Now suppose you have an angle that is odd under time reversal. So time reversal takes theta to minus theta because electric fields are even and magnetic fields are odd under time reversal. So what angles satisfy theta equal to minus theta? Well, theta equal to 0 is the easy one, and theta equal to pi is the slightly less easy one. So you could have theta equal to pi materials and theta equal to 0 materials, which we now call topological and ordinary insulators, effectively. And from band structure, you know, the way we thought about this starting in 2006, we and two other groups, was that there seem to be two kinds of insulators when you look at topological classification of band structure, and they are distinguished by their Dirac cone surface states, where they have an even or odd number. So I want to explain how electrodynamics and Berry phase lets you connect Wilczek's picture to the band structure picture. So the way that the number of Dirac cones on a metallic surface state is related to the theta angle gets into what is this the total derivative of. So this is going to be a fairly quick summary of something that took many of us several years to work out. So don't be alarmed if it seems, you know, too quick or something. It's not as obvious as I try to make it seem here. This E dot B, that is a total derivative of ADA, if you want, which is the electromagnetic signature of the quantum Hall effect, or a Hall effect at a surface. So in other words, to say the material has a theta angle in the bulk, and outside there's some vacuum with theta equal to 0, means that at every boundary between them, there will be some Hall layer. The Hall layer could be any integer. I'm allowed to have a two-dimensional system with an integer Hall effect that's insulating. But then theta over 2 pi gives me sort of an offset to the integer. So if you like, the way that generates a magnetoelectric effect, which is the sign of E dot B, magnetoelectric effect can be apply electric field and measure magnetic moment, or apply magnetic field and measure electrical moment. Suppose I apply an electric field, then I get currents that run around these quantum Hall layers, and those produce a magnetic field. So basically, this will hang together if a material with an odd number of Dirac cones on the surface, which is how we originally thought of a topological insulator, is somehow connected, if I could make the surface gapped, to a material with a half integer rather than integer Hall effect. So one Dirac cone becoming gapped has to give me not an integer Hall effect, but a half integer Hall effect. And that, it might sound bizarre, but that was one of the key experimental measurements that let people know that graphene was magical, was really Dirac cones. So graphene has 4 Dirac cones once you combine 2 locations in the Brillouin zone and 2 spins. And the way people knew that graphene was not like any other integer quantum Hall material is that when they went and measured the integer quantum Hall effect in graphene, and it's really beautiful in graphene, by the way, it survives to very high temperature and very high field, you don't see 0, 1, 2, 3, 4 times e squared over h. You see -10, -6, -2, 2, 6, 10, at least if the interactions are weak. Now you can see lots of fractional plateaus and so on. But those numbers, those are 4 times the half integers. In other words, if I divide by the 4-fold degeneracy of the Dirac cones, this is saying that 1 Dirac cone, if I put it in a magnetic field and gap it, would indeed give me a half integer. So at least the connection between what Wilczek did and what we and others did works, but there's kind of a neat microscopic gauge result that comes out of it, which is a new way to write the Z2 invariant. So I won't write the Z2 invariant the way we originally worked it out because it's kind of ugly and doesn't have a very beautiful interpretation in terms of particle physics quantities. But let me tell you, and the star means I'm not even going to try to derive this formula, but I'll just say a bit about what it means. The way things hang together, if I look at in any 3D crystal, if there is a piece of the magnetoelectric term that goes like E dot B, I could measure that as magnetic field induced by electric field or electric polarization induced by magnetic field. And what computes it microscopically from the band structure is the Chern-Simons form of the Berry phase. So in other words, the same script A as before, except it turns out this has to be non-abelian. And one thing for all the field theorists in the audience, the Chern-Simons form has a bizarre property that under large gauge transformations, those that are not homotopic to the identity, this integral shifts by a quantized amount, basically enough to shift theta by 2 pi. So the 2 pi ambiguity of theta is a well-known property of the Chern-Simons form. So that kind of says that something about the non-abelian gauge field in every material matters for its magnetoelectric properties. And we went ahead and spent a lot of time thinking about that, and we have not found many other examples of the non-abelian Berry connection being important, but maybe you will. So in other words, my claim is that for that Chern-Simons term to do anything interesting, I actually need multiple occupied bands, and yeah, here's my, we can make other related uses of it, but I don't know many other quantities in physical dimensions controlled by the non-abelian buried field. One maybe general comment, there are many quantities that have a geometric piece and another piece that is more standard quantum perturbation theory, and only with an extra symmetry do you rule out the other piece. So electric polarization is special where the only piece is the Berry phase piece, but here there's a non-universal or non-geometric piece that happens to vanish if you have time reversal symmetry. And to convince you that we do some work for a living, this is a fairly long perturbation theory calculation from Andrew Essen and Ari Turner and collaborators. All right, so now I want to come to the modern era and try to do something with metals. And it turns out that the Berry phase and what it does in metals is often cited as the biggest missing thing in like our classic solid state physics books that we learned from when I was in grad school. Books like Ashcroft and Merman will talk about the semi-classical dynamics of electrons in a crystal, but they won't have this second term, and that F is the same Berry curvature, and this is dk by dt. But having this term makes everything much more beautiful. So just in case you're not a solid state physicist, the first way we describe metals is we think about electron wave packets moving sort of semi-classically through a metal, and the fact that it's in a crystal rather than in vacuum gives me a modification of the electron velocity. So for example, the effective mass of semiconductors and why silicon and other materials, if you want to get their details right, you need to use the right group velocity in this first term. But if I were to look at like the Lorentz force on the wave packet, the Lorentz force has an E plus V cross B term. There are 2 terms in the Lorentz force, but there's only 1 term in the velocity. Well, maybe not. It turns out that if you go into general crystals, this second term is there unless I have both inversion and time reversal. And understanding this is kind of a sad story, and that Karplus and Luttinger knew a long time ago that there had to be something like this back in the 1960s, but no one really believed them, or at least believed it could be physically important because they didn't have the sort of modern Berry phase language to explain what this object was. But in hindsight, what's going on here is sort of that as the electron changes its wave vector, its momentum, it has a different spatial structure, and that spatial structure might move within the unit cell. It might be moving from atom A to atom B. That's kind of an anomalous velocity. That's this extra term, ordinary velocity, anomalous velocity. So I'm going to say a little bit about uses of this equation to try to measure the Berry phase, because that's how we first got interested in metals. But the standard assumption would be that, and I think it's true, that in ordinary metals, non-semimetals, the effect of this nice term is that it gives you interesting things, but they're not quantized, because in a metal, you can always change the Fermi surface by just a little bit. And most things will change when you change the Fermi surface by just a little bit. So you need special cases where this gives you something that's actually quantized. But the reason why people originally cared so much about it, like back in the 60s, was it does underlie the Hall effect in metals like iron and things like that, the ordinary, more or less classical Hall effect. And just to kind of try to give you a little bit of a picture of how what happens in insulators hangs together with what happens in metals. If I were to look at the formula for the polarization of an insulator, that's like a loop integral of A. This is just writing out that Berry connection A. That suggests that something about A is related to where the electron sits in the unit cell. And then a change in A, like dA by dt, would be a velocity, because that means the electron is moving within the unit cell. And then dA by dt, well, that's like dA by dk times dk by dt. And that's more or less exactly this anomalous velocity term. So something about the total derivative of the polarization, if you like, is why I needed to have that extra term. And there's somewhat, deeper things related to symmetry about when we expect that Berry phase to matter. Basically, broken inversion, which is key for a lot of optical effects, is a very good sign that something about the Berry phase is going to matter. So why people cared, as an example of a hard, messy problem, if you just thought about, as you make a metal like iron, say, go from dirty to clean, you wind up with maybe 3 regimes of the Hall effect. If it's very clean, you get what's called skew scattering, which is like ordinary theory of transport, stuff at the Fermi surface matters. If you make it very dirty, you get things like localization. But there's a big range in between where the dominant contribution of the Hall effect is just the same integral that we do for the quantum Hall effect, except it's not quantized because we only integrate over the occupied Fermi sea. And this is a sign that it was an old and hard problem, that even by the time they get to figure 47 of this classic review, it's still a speculative and schematic phase diagram. There's no small parameter or anything, but this seems to be how many metals actually work. The great thing about semimetals is that things like graphene, they're a lot simpler and more elegant in some ways. So we got interested in trying to find a cleaner experiment, one where you didn't have to go to this intermediate range. Could we find some other way where that Berry curvature was measurable in a metal? And we were partly motivated by a very old series of experiments where the experimentalists did something very honest. They had a picture in terms of spin-orbit coupling for many years, and then they did the experiment in silicon, which, because it's a light element, has very weak spin-orbit coupling. And then they decided, well, maybe our original explanation doesn't quite work, and we don't know what the new explanation is because the effect is just as strong in silicon as in heavy materials. And the experiment that they did is something called the circular photogalvanic effect, or chiral photocurrent. And I will quickly tell you about the semi-classical version, because this is where we started getting interested in the problem before realizing that this effect could be a lot more interesting in other materials. But basically, the idea of this effect is, if I look at an ordinary metal, like a 2-dimensional metal, let's say its ground state occupancy is the black circle, and then if I apply an electric field that pushes the electrons a little bit away, eventually some scattering keeps them from moving too far away. So that's this gray circle. And then because the light is circularly polarized, the gray circle moves slowly at low frequency around the black circle. So the ordinary velocity, you can kind of see, will average out in that process, but the anomalous velocity, if you have a low symmetry crystal, will not. You will get a net current that is one way for right circular polarization and the other way for left circular, and that's the chiral photocurrent or circular photogalvanic effect. So pretty simple, just some classical, differential equations, and you get it. It's now called the nonlinear Hall effect, and generalized to 3D by Soderman and Fu. So that's where things sat for us until some big material science discoveries. And this is the discovery I was mentioning that theorists had the idea back in the 1930s. You might have heard that the theoretical idea of graphene was worked out in 1946. Well, even older, very soon in the early days of quantum mechanics, was the idea that there ought to be some very special semimetals, even in 3D. And the basic idea was, soon after Dirac wrote down his Dirac equation, people realized two ways to take half of Dirac's equation, which in our kind of condensed matter language would be a four-band problem. In other words, it's a 4x4 matrix equation for an electron and its antiparticle, say. And we found the first examples of Dirac semimetals, in other words, four bands coming together in a semimetallic point at the Fermi level, just around 2013. Very soon after Dirac, something that's almost a bit simpler, Weyl pointed out that the other way, one of the two ways to take half of the Dirac equation is to imagine massless particles that have only one-handedness. So like a left-handed particle, which means the spin is, say, against its direction of motion, and a right-handed particle where the spin is along its direction of motion. There's no way to catch up with the particle if it's massless and flip its helicity. So for massless particles without extra symmetry, the Dirac equation naturally separates into left-handed and right-handed pieces. These don't seem to exist in the standard model, but they do exist in condensed matter circa 2014, 2015. If you want, the other way to take half of the Dirac equation was the Majorana way, which is to say that maybe the particle and its antiparticle are the same thing. We're still wondering if the neutrino, for example, is a Majorana fermion. So the way that this became sort of topological and that contributed to their being found experimentally was that if you look at one of these two-band crossings, a so-called Weyl point in a crystal, each one of those has a topological charge. It's basically a monopole of the Berry curvature. If I made a little sphere around one of these points, then, well, I'm in a three-dimensional material now. The sphere is two-dimensional, but the integral of the Berry flux through that little sphere is an integer, and that's the Weyl charge of the Weyl point. And a nice theorem from particle physicists, Nielsen-Ninomiya, tells us that the total Weyl charge of all the Weyl points in the material will be zero. But a neat way that that translates to condensed matter, if I go to a surface of a material with these Weyl points, they're actually arcs. There are Fermi surfaces on the surface, two-dimensional Fermi surfaces that are not closed surfaces, they're just arcs. Basically, you could have one piece of the surface here and the connecting piece down on the bottom. So it's a very unusual kind of Fermi surface, which is what people found in photoemission to convince themselves that they'd finally found Weyl fermions. So even if they're not there in the standard model, they do exist in tantalum arsenide and so on. And then once people find the material, you could ask, what do these materials do? Is there some consequence now that you've got a new material, new kind of semimetal, which is kind of like a 3D version of graphene? So this is an effect of linear optics that is approximately quantized in graphene. I'm going to claim, although it took us a couple of years to get to this, and it wasn't like a very we didn't think about it the right way to begin with. I think that's the way things usually are. But there's going to be a nonlinear effect in Weyl semimetals that is quite special, that I want to sort of explain the path that led us to that. And then I'll be pretty much done with the main scientific content for today. So where many physicists got excited after the discovery of Weyl semimetals was based on nonlinear effects because of something called the chiral anomaly in particle physics. So if I just had one Weyl point, the world would be somewhat problematic because I could apply electric and magnetic fields and spontaneously produce charge. So anomaly is like another word for problem, more or less, or violation of a symmetry. So if we believe that charge should be quantized, then the Nielsen-Ninomiya theorem is good because it means that even if I create charge at one Weyl point, I will annihilate charge at the other. So effectively, by applying electric and magnetic fields, I will pump fields from one to another, pump current from one to another. But it turns out that we think the observable effect, for various reasons, is not E dot B. There's an E squared effect that is observable. And just by power counting, in hindsight, we could have guessed what that effect might be. So suppose you wrote the quantum Hall effect just counting dimensions and not worrying about what material makes it happen, or about whether it's longitudinal or transverse or whatever, then you would say the quantum Hall effect is something where you create a two-dimensional current density by applying an electric field. Well, if you wanted something that was quadratic in electric field, effectively the chiral anomaly would be like dn dt. You create charge at a rate that is EB plus some factors. So creating charge is difficult, at least for most of us, I think. So, but you can create current when you shine a light on a material. So maybe you could find a material where current injection, just like the rate at which you add current to the ground state when you first shine light on a material, goes like E squared, electric field squared, and then you would need to add some factors. You would need to add 1 over time and 1 over length. So now this has to be a three-dimensional current density, and it would have to go like charge cubed over h squared. So is there any material where that's going to happen? So it'll turn out to be Weyl semimetals, but before we got to that, there was a big, long debate about linear optics in Weyl semimetals and whether there was sort of a chiral magnetic effect in linear optics. And I think the consensus now is no, but understanding that was productive. I mean, here are papers sort of wrapping that up. Understanding that was still productive in solving an old problem about optics. So I'll tell you the story briefly. Basically, there was the idea that if I just applied a magnetic field, I could create a current. This would be like an E dot B effect, except maybe the electric field could be provided by the material in an inversion breaking material. Now, at equilibrium, I think everyone agrees that this should be zero, because one difference between magnetic and electric fields is that in a magnetic field, a system can reach a new equilibrium. In an electric field, it will keep pushing a current. But there's the general belief that there is a steady state in a magnetic field that will not have a macroscopic transport current density in bulk. Obviously, you can have persistent currents in a superconducting ring or something like that, so you have to be very careful in defining things. But if you go to non-zero frequency, people realized that you could get a current, and they were excited that maybe at non-zero frequency, like an oscillating magnetic field, you will get a current that is somehow related to the chiral anomaly. It turns out that it's not related to chiral anomaly, and it's not related to Weyl fermions in particular. It comes from we call it the gyrotropic magnetic effect, and it comes from the integral over the Fermi surface, natural thing to do in a metal, of the orbital magnetic moment of the Bloch electron, which is another kind of geometrical quantity that I'll write up in a second. But basically, this says that you measure something, whenever you watch light get rotated through a chiral material, through a chiral crystal, like quartz or selenium, then at least at low frequency, there is a piece that comes from something geometric. So another example of these geometrical quantities, but it's not the Berry phase. It's something closely related, and to understand why this happens, it's just one slide in hindsight. I mean, we did like 8 pages of quantum calculation supplemental material, but in the body of the paper, we just give the simple semi-classical picture, which is basically this line at the bottom is saying that in addition to that anomalous velocity I talked about, there's another modification you should expect even in the group velocity, and that is if I put on a magnetic field, well, electrons in an atom have a magnetic moment, why not in a crystal? And in a crystal, you'd expect the magnetic moment to vary with the momentum, because we know that different momenta mean the electron is sitting on different atoms and has different orbital structure. So basically, the k derivative of that gives me a group velocity. In other words, in a magnetic field, the velocity of electrons at k is changed because there's a k derivative of m. And if you're wondering what m looks like, it looks a lot like the Berry curvature, but with an extra power of energy sandwiched in between. So it's got an energy, it's not purely geometric, but it clearly has some close relation to the Berry curvature that I will admit confused us for a while. So anyway, this is saying that the chiral rotation is not actually specific to Weyl semimetals and not even particularly large in Weyl semimetals. So we have to go to nonlinear optics if we want something interesting to happen. And the good news is, from an experimentalist, this is a paper by my colleague at Berkeley, Joe Ornstein, and he claims it's the first time in his life that he just stuck something in his experiment and he measured it, and it was so large that he had to adjust the sensitivity down of the experiment. If you take tantalum arsenide, this newly discovered Weyl semimetal, and you do one of the first nonlinear optical experiments that anyone does, which is shine a laser on it at frequency omega and measure the light that comes out at frequency 2 omega, you realize that in a sense, these Weyl semimetals are about the most nonlinear optical materials that we have. If you want to put that in terms of a coefficient to compare to different materials, this is just room temperature. You know, he would admit that it's not nearly as hard as the other experiment I'll tell you about. At room temperature, you get at least a factor of 10, and if you're allowed to change the frequency, even a factor of more than 10 in the strength of nonlinear optics in these materials compared to the ones we actually use in applications like barium titanate. Now, the disadvantage is this is a semimetal, which means it's somewhat lossy, while an insulator is not very lossy. So if you don't care about maximizing the effect, you just want to maximize the efficiency, you would use barium titanate. But sometimes, especially in physics laboratories, you just want the frequency double in the minimum amount of material possible, and then this tantalum arsenide is actually useful. It's a fairly complicated material. It is kind of the benchmark Weyl semimetal. It has 24 Weyl points, but maybe we could find a simpler material that would do something a little bit more interesting from a fundamental point of view than just being a large number. Why exactly this is so large is kind of an interesting question that has bedeviled us for a few years. I don't know a very good answer, aside from that's the way. I guess it's very strongly polar in some sense, and we have kind of a sum rule to relate it to the shape of the wavefunctions, but it doesn't seem to be for any very deep reason. So again, this is the circular photogalvanic effect. What I'm going to claim is if you take this same effect and do it at higher frequency in the right material, you will get something quantized in the right Weyl semimetal. And that gives you, the quantization is not going to be great. It'll be within a factor of 2 or so, but the natural scale will be fundamental units, and I'll talk about why it reveals that graphene is kind of lucky if I get to that. So I want to do that same experiment of circularly polarized light, and the way these Weyl materials work, if it's a chiral Weyl semimetal, which means it has kind of low symmetry, rhodium silicide will be the magic material for the experiment, then it will have positive and negative Weyl points. These are the monopoles and anti-monopoles of Weyl charge. And again, the Weyl charge is made up of that Berry flux. They'll be at different energies, and one of them could be occupied below the Fermi level, which is this line, and one of them could be unoccupied. And now if I think about what practical optics does, when I shine light on that, I get optical transitions across this Weyl point, but not across that one. They're so-called poly-blocked because the final state is filled until I increase the frequency of the light enough that this one becomes active as well. So in other words, in this picture of a chiral Weyl semimetal, there'll be some range of frequencies when I only get transitions across one Weyl point, some when I get transitions across both of them. And if I were at very low frequency, say, so I wasn't crossing either one, then it would be sort of in that semi-classical limit where we don't need to worry about the Weyl point, and our calculation from 2010 works, and we know how to get the effect, and it's not very large. So the magic is, if you cross the Weyl point, the effect is both about 100 times larger than the semi-classical effect away from the Weyl point, and it's actually quantized. So I don't know a way to do this experiment in particle physics if it turns out that the neutrino is a Weyl fermion, but in a solid, it's not that hard. You shine light of intensity I, and you measure that the rate at which you inject current, the difference between right and left circular, is proportional to an integer, which is the Weyl charge of the Weyl point that you're crossing, times e cubed over h squared. And just note a couple of things. One is, this is sensitive to the sign of the integer. So in other words, the top point here and the bottom point here will have opposite contributions and will cancel each other out once the frequency is high enough. And then, after we predicted this, we had a material that turns out to be hard to grow as crystals, but Zahid Hassan's group at Princeton found a material that not only has the right symmetries and a pretty large energy splitting between the Weyl points, it's got a Weyl charge of 4. It's so-called multifold Weyl semimetal, so it helps a little bit in the strength of signal, and then a nice paper that sort of gave details of how strong this should be and what the frequency dependence should be and so on. This is gyrotropic magnetic effect, the linear effect, and this is quantized circular photogalvanic effect, was this paper. And basically, if you had to take one number away from this picture, it would be that the energy splitting here is about 0.7 eV, meaning that you will get a strong effect from crossing just one point, from low frequency up to about 0.7 eV, and then it should be, in principle, canceled out by this other point. So then they do the experiment, which is quite clever. And here, I think maybe in the interest of time, I won't talk too much about the calculation, but if you're a graphene expert or a Fermi's golden rule expert, you'll trust me that this is not all that hard. I mean, maybe the magic, let me explain the part of it that is a little bit surprising is that you'd say, well, if I go back here, if I'm doing like Fermi's golden rule perturbation theory, I've got initial states and final states. Nowhere does the vowel point appear in the direct perturbation theory. But it's a lot like what Thouless did, where you start off with standard perturbation theory and you realize that there's some geometry or topology hiding, because the fact that the vowel point is topological or has a charge means I couldn't just open up a gap here. There has to be some relationship between the upper and lower states that keeps me from just opening up a gap, if you like. And indeed, when you do the integral over initial and final states, you can transform it to an integral over the magic sphere, and that gives you that topological integer. So, a few more details. This is kind of the idea. So I think I'll skip the mathematical details, but all of these calculations are essentially just perturbation theory and recognizing the right geometrical objects in hindsight. Here's the experiment, and the idea was to do it all optically, which makes it a little bit hard to measure the magnitude, although other groups have tried to measure the magnitude since then. If you shine light in with a laser at high frequency, you might be able to drive a brief burst of current through this current injection mechanism. And in practice, the current is kind of into the sample. And that little pulse of current will radiate out basically a frequency related to the envelope of the initial one. So you'll get terahertz light out of high frequency light in, and you can measure quite easily what is the frequency dependence of what you get out. And here's the experimental paper from 2020. And the work since then by other groups, especially at Penn, has been able to say something about the magnitude, that it's at least consistent with e cubed over h squared. But basically the data that made us celebrate a bit, the laser starts to fail below about 0.5 eV, but this is that strong signal that suddenly drops off at about 0.7 eV, the predicted value. And that's nice because this is not how nonlinear optics generally works. You would generally expect things to kind of go up or have resonances or whatever. This sort of plateau structure, which we think is from one vowel point, dropping off at just the frequency when it's supposed to hit the other vowel point, is maybe the neatest demonstration that a vowel semimetal really has these bulk points in it controlling a physical response. So I'll say now the caveats, and this is maybe a motivation for why we do many-body physics rather than just one electron physics. When you add interactions, this is not like the chiral anomaly or something, or the quantum Hall effect. It gets interaction corrections that are finite. And we did a bit of work on those, and we think that the quantization gets corrections that are of order 50% or so. The same thing is true with linear, and this is what I meant by saying that sometimes graphene in particular, maybe the universe in general is more elegant than we imagine, but graphene in particular always seems to be the one material that behaves better than you would expect based on simple principles or dimensional analysis. If you calculate the size of the correction in graphene, naively the correction would be of order 50% or something, and the quantization wouldn't be nearly as good as what you see. But after many years and many groups doing the calculation carefully, they figured out that there's a small number in the interaction correction, and that explains the experiment. And the small number is just that the coefficient, adding up a couple of diagrams, is 19 minus 6 pi. Think about what pi is, that's pretty small, and divide it by 12. So a number that you would, as far as I can tell, you would expect this to be an order unity correction, but it winds up being a 1% correction because 19 minus 6 pi is small. I don't know if that's some kind of cosmic joke or something about graphene. Maybe there's a deeper reason, but we don't know it. But we don't get any kind of magic like that for the vowel semimetal, so the correction is not that small. So I think that sort of wraps up the main technical point I wanted to make. I have a couple of Outlook-style comments, and then I'd be happy to have a bit of discussion. But basically, one quick indication of where the field is going. So far I've mostly talked about just standard optical experiments where the material is in its ground state and you hit it with light. But an enormous bit of progress experimentally where we kind of need more theory is in so-called pump probe optics, or driving the system and then measuring optical properties and seeing new states of matter or whatever. And a simple example is to use currents to break symmetries. So for example, if you started with a Dirac semimetal, you can sort of turn it into something more like a Weyl semimetal by using the current to break the symmetry. Basically, if you took a Weyl semimetal and you had both inversion and time reversal, then it turns into Dirac because the two Weyl points come together. But you can break that, and this is just one example of how it's possible to manipulate materials in new ways, but we don't have great theoretical techniques because these are often kind of far from equilibrium problems. We often have to do some kind of simple picture. So to sort of summarize, before I come to the maybe overview comments, nonlinear optics in Weyl semimetals is strong in like the standard material tantalum arsenide, but I think that's just because tantalum arsenide is very far from being inversion symmetric, and it has very lopsided or highly skewed electronic orbitals, is the more precise statement. If we go to this other material, rhodium silicide, then there is a quantized nonlinear optical effect, the first such effect. And quantized is a strong statement. Maybe a better way to put it is the natural scale is e cubed over h squared times an integer. And that lets us add something to our kind of integer quanta and electromagnetic response. So if you want the Josephson frequency and the flux quantum are linear in charge, the quantum Hall effect, magnetoelectric effect are e squared over h. Graphene optical transmission is e squared over h with a factor of c if you want. And then this Weyl semimetal is a root to e cubed over h squared. If you wanted to keep going to more and more, well, you need more powers of space and time, so you'll need to find probably a harder experiment to do. But it does seem like this principle of geometrical quantities leading you to quantization still might have some room to run. So I put two slides at the end, and this is intended partly to kind of spur discussion, partly since I'm giving two more lectures. I didn't want to exhaust everyone with any more technical details, but these are a bit on things that have developed since I was a student, aside from the more many-body things I'll talk about later. Maybe if the electrons are nearly independent, that's a relatively easy problem for sort of pencil and paper. So if you like, the point of this talk was by thinking about the geometry in the right way and thinking about objects kind of inherited from particle physics, it seems that those same structures give you a lot of interesting properties in materials. And maybe our most recent effort to kind of find new objects and explain nonlinear optics and so on is in this thing we just posted. And the basic idea is, as you get to higher order optics and so on, there's some Riemannian geometry. There are more and more quantities expressible in terms of projection operators. They have some physical applications. You can sometimes relate excited states to ground states, which is a so-called sum rule. So one brief aspect, I mean, the curvature and things like that appear in this problem are also in many cases defined for many body states. So for example, famously, the quantum Hall effect, you can generalize the Berry curvature from a one electron property to a kind of Berry curvature of all the electrons. That was done by New, Thouless, and Wu, but we can't do that for all the geometrical objects. So I think one hope I have is that, as we get more geometrical objects that do something useful in the one electron case, understanding which of those give you new states or new effects in the interacting system is kind of an important problem. And then finally, in addition to standard observables, a little bit of geometry of entanglement and things like that have already come up in the workshop, and I will try to say a little bit about those later on. But I would say it seems like there are natural geometrical objects in quantum mechanics, and I tried to introduce you to a few of them, but I don't think they're limited to one electron in crystal. That's just the most pedagogical case I could think of. And then my second kind of closing slide is a couple of things. One I already mentioned, and then the third is something that has changed in how I discuss physics with my students. So one is, once we start to add interactions, we can make a lot of progress near equilibrium because we've had to, because that's what a lot of condensed matter theory has been about for many years. But there are many more systems that are out of equilibrium, and indeed quantum computers, for example, we'll see in the next lecture, naturally function out of equilibrium. Getting to the ground state is generally very hard. So we sort of need new theoretical methods for far from equilibrium physics, at least once we're away from one electron. A lot of what we do are either very simple models or very complicated numerical calculations whose impact for theory is not that clear. But there's so many experiments. People build these billion-dollar light sources, for example. I think getting more science out of those is kind of a challenge for theorists. And then maybe the most immediate challenge, not at the billion-dollar level, but people build $100 million quantum computers, and those are also naturally suited to dynamics. So it's time to move condensed matter theory out of equilibrium. And then finally, what I meant by a change when I talked to my grad students, we used to have a great focus on figuring out what's the right Hamiltonian for some material, some local two-body effective Hamiltonian description. And we fight about, how important is the Coulomb interaction? Is it screened or whatever? It was more fun to just pick your own Hamiltonian and show that it did something fun, but we used to look down on that. But now, with the power of quantum computers and emulators and so on, and also with the power of kind of non-standard Hamiltonians to teach us new things, now the question has shifted a bit. So if you like, we've had a focus for a long time in condensed matter on states that exist under local two-body interactions. But if you ask where neat ideas are coming from, there are the various Kitaev models, which have 4-spin or higher interactions, or string net models with 6 or 12 or however many spin interactions. There's Sachdev-Kitaev is kind of a long-ranged all-to-all type model. So either infinite dimensional or zero-dimensional, depending on your preference. Those non-standard Hamiltonians and non-standard states have been teaching us a lot the last 10 years, and it's clear that maybe our focus on, as Larkin used to say, what is the form of the Hamiltonian as the first question, that's no longer the first question. Now the question is, now that we can build almost any state we want, what should we build? Because if you look online, the amount of control that people have over reasonably large numbers of qubits, so maybe perfect control with very small errors over still only 20, 25, but a reasonable level of control, enough to do calculations that we'll say in the next lecture with maybe 100 qubits. We need problems, what kind of states out there would be the best possible sensor or the best emulator of a black hole or whatever. So I think one reason why I wanted to be at this discussion meeting is that I feel like the kind of question we need to address in quantum condensed matter, we're being forced to dream a bit bigger than we did before because we can make much more than we ever could before. Materials are still a great guide and they still do beautiful things, and I'm still at heart a quantum materials person. But there is really a new era of kind of designer quantum matter, or maybe matter is not even the right term, designer quantum states. So I hope that some of you will be involved in asking the right questions to do with that. So with that, thank you very much, and I think I'll stop there.
Thanks, Joel, for a great talk. Just a very quick question. Would there be any optical analog of the fractional quantum Hall where things are special fractions rather than integral?
Yeah, I mean, it might be quite subtle. So optical experiments have been sort of important for quantum Hall, but generally the problem, if you like, is that they couple directly to the charge, and the direct signatures of anyons in optical effects are not very clear. What you tend to measure is some kind of collective mode that's more an electronic mode than an anyonic mode is probably how I'd put it. But for example, something that's gotten a lot of press recently, there's a spin 2 mode in condensed matter called Gervin-McDonald-Platzman mode, but you could also call it a kind of emergent graviton. So people have talked about measuring that with optical type experiments. Yeah, that's right. I mean, it's related to the way it couples to the anisotropy, say, in the underlying material is somewhat reminiscent of gravity. I mean, it's a pretty poor man's version of a graviton, I would say, but there is at least something there that has a little bit of the same mathematics. But yeah, for fractional quantum Hall, I mean, I think there's a lot that can be done with out of equilibrium experiments. Actually, we heard a very nice talk today by Yuval Geffen, which was on seeing anyons through kind of 2 leads coming in a sort of out of equilibrium way. But I don't know that optics is going to be the most practical way. However, I mean, I will say that probably the biggest excitement experimentally in anyon physics in the last year or two is what's called the fractional quantum anomalous Hall effect. So anomalous there means it happens in zero magnetic field. Like usually in the quantum Hall effect, we have to put on some giant magnetic field. But people have realized that in a variety of two-dimensional atomically thin van der Waals materials, you can get fractional quantum Hall states in zero magnetic field. And at least the first group, one of the first groups, but maybe the first group to do that was Xiaodong Xu at Washington doing it with optics. He had kind of a clever technique, which is related to something called the Strata formula, to sort of measure compressibility and realize when you were on a Hall plateau, even without having to make contacts. But yeah, direct detection of anyons, that I've not seen a good optical proposal yet.
In the response for the 3D topological insulator, you had theta being quantized to pi because of time reversal symmetry, and then you argued how that results in a half quantized quantum Hall state on the boundary. Yeah. But if I explicitly break time reversal and tune theta away from pi, it seems like I still have some kind of an improperly quantized integer Hall. But,
definitely.
But without having any topological insulators. So.
No, that's right. I think Axion electrodynamics with a non-quantized theta doesn't depend on having topological materials. In fact, maybe two comments on that. There's a material that is sort of the benchmark for accurately measuring surface Hall effect in an insulator, which is CR203. And this is a good material because it has broken time reversal and broken inversion. So it allows theta to be anything, but it has enough symmetry that you don't get the terms other than theta. You don't get E cross B or something. And it has theta, which is not quantized. I mean, it's roughly, say, pi over 24, but not in the sense of this being some integer. So I think you're right that in general, if I don't have any symmetries, theta will not be quantized. And that's maybe why that's okay. This kind of fractional surface theta or offset doesn't indicate fractional particles. There's no fractional charge associated with this. Really, the way to think about it is just, it would be like I took a little, okay, the polarization analog would be, without fractionalizing charge, I could have E over 3 localized in a region up here and minus E over 3 localized in a region down there because the total charge was conserved. And that's a little bit like what happened here. It's relevant that theta is positive here and theta is negative there. The math of it is kind of cute. It's just that F wedge F, this E dot B term is the derivative of AF, and AF is a quantum Hall layer. So you really, in principle, you couldn't tell whether your material had a bulk theta or whether it had integer quantum Hall layers at the top and bottom if theta was an integer. But if theta is fractional, there's no way to make kind of a fractional surface layer like this. One recent discovery is what are called magnetic topological insulators or antiferromagnetic topological insulators. So you could have other symmetries that quantize theta besides time reversal. So an easy one is I could have the product of time reversal and some lattice translation. Let me write it that way. Or maybe if I took some kind of simple picture of an antiferromagnet, that breaks time reversal, but if I time reverse and move by half the unit cell, then I'm back to where I started. So theoretically predicted, a student of mine, Roger Mong, did a lot of work on this. Starting around 2010 was this possibility that you could get theta equal to pi in a magnet. And there were two papers in Nature in 2019 reporting that MnBi2Te4, so-called MBT, which is a hard material to grow, but it turns out to be the first example of a magnetic topological insulator with theta equal to pi.
But in that case, the CR203 case, would it be correct to conclude from the fact that you have surface quantum Hall effect that there are surface modes?
I don't think so. I guess my statement would be that if you have one surface which is plus theta and one surface which is minus theta, you can have it be totally gapped all the way around with no edge state or anything like that. So it really is in that case, I would think of it as a different from like an integer quantum Hall surface layer, which will have edge states and other excitation properties. So this is more, I mean, a lot of these things have kind of an analog in polarization where you can have polarization, when you think about measuring it, you could define polarization as either electric dipole moment, per volume, or surface charge density per area. And those two are sort of related, but if you took a material with some dipole moment density, it'll have positive surface charge density sigma at one side and negative at the other side, but those will be some fractions. It doesn't really mean that there's any fractional charge in the system. It's just that you kind of shifted everything over by a bit. So I guess polarization and theta, I do feel that people in my field are sometimes deliberately trying to make theta sound like something that only topological insulators have, when it was known and measured before in materials like this chromium sesquioxide. But there are special things. I mean, having a quantized value is nice, but yeah, I think you can have it in much the way you can have a fractional polarization without it meaning fractional charge. So I will say that in this case, there is an aspect that is geometrical, at least, in every material that has a theta angle, because inside this, there is a piece that comes from that Chern-Simons integral. But there are other pieces as well. Well, if I took, a theta equal to pi material, then the only piece is the Chern-Simons integral.
Yeah. So I had two questions. One was, like you said, like from the Josephson and the Hall effect, you can get E and H, right? And then you talked about the light transmission is also kind of, it seemed to be quantized, but is it so sharp that you can also get like the speed of light from that? I mean,
I think so, but only to about 1% accuracy. Because the graphene quantization, I think quantization in semimetals is, as far as I can tell, I don't know any example where it's really precise in the sense of like arbitrarily accurate. While insulators, we know it can be extremely accurate. So I think you could get C, but only to about 1% accuracy.
question was you talked about the correction to the semi-classical equations. And so do those for example, say anything about like edge states and so on, there are the skipping orbits and so on in class, like purely classical. So do these give any insights into those?
That's interesting. I don't know a way to connect that Berry phase term in the semi-classical equations of motion, because I don't know how to write that. I mean, there's a little bit of work on this, but I don't know a way to use it to get skipping orbits. So to do that, what you would want, if you want like, this semi-classical term is happening because of K-space being non-trivial in a crystal. And then to see the edge, you also want real space to be non-trivial, because you want to have a boundary. So how to modify those semi-classical equations when you have a boundary, I haven't seen. I have seen people think about if you have like weak variation, and maybe something like that could give you the skipping orbit. But I don't know, like an abrupt boundary with the collision, I mean, that I'm not quite sure. I mean, I guess I can imagine if you're willing to make a very simple model of the boundary, I guess, where electron comes in and bounces off it. I mean, you can get the equivalent of the Lorentz force out of this. So I think if you're allowed to not treat the boundary very seriously, I think you could get it. But then it would just be like the normal skipping orbit picture.
Don't give anything like the extra part that you added, would that give anything, give any more insights? Like,
yeah, I don't think so. I mean, it does give insights into a lot of things that I didn't talk about. You can go to like, okay, the case I know where it's been studied a bit, and I'll mention one recent paper by a group at Illinois. So if you like, ordinary Hall effect would be at wave vector equal to 0. It's kind of long wavelength property. If you go to one ordering Q, you get that gyrotropic magnetic effect I was talking about. So we're kind of thinking about spatial variation simpler than an edge. Let me just think about finite wave vector. Order Q squared is something we worked out, and then Barry Bradlin's group at the University of Illinois figured out a way to do kind of Berry phase contributions to responses at arbitrary finite wave vector in a crystal. So it's still not an edge, and I don't know how the edge would be modified, but at least you can do some kinds of spatial variation quite well, but it's all these like periodic variations.
Joel, this is more about the last outlook things that you were trying to get at. So you were trying to go from some sort of a single particle picture where some of these are much better understood to trying to talk about whether there will be many-body analogs and so on. So one question would be, do you think this would gradually go from, let's say, one particle density matrix to two particle density matrix to 3 particle, looking at those would be useful, or you should just look at the full many-body eigenstates and think about those things?
Yeah, I mean, the cases I know where it works out nicely, it's the second, where you just go directly to the many-body eigenstate. And maybe just in the interest of pedagogy, an example of how that works is, if I were to look at this topological integer n for the quantum Hall effect, that's going to be something like d2k over 2 pi. I could write it as, if my Bloch state is sort of uk e to the ik dot r. So that would be like writing it in terms of a 1 electron Bloch state. And then the point of this many body rewriting is suppose that instead, or let's call it psi is some many body wave function of a bunch of electrons. And the geometry is that I think about a torus with 2 fluxes through the 2 great circles of the torus. And then the response of phi to those 2 fluxes, I can write very much the same integral, and it will give me a definition of the many-body invariant in terms of the many-body wave function. So in other words, I could write sort of n as, and it will reduce to the sum of that over occupied bands if the many-body state is a Slater determinant of some occupied bands. So I'd have like d2 theta, again over 2 pi I. And now it's the same object. I won't write out the whole thing, but it's the change in the many-body wave function with response to boundary fluxes. So this is called the flux trick. And this works for some topological invariants, but not others. I think it's true that there is very nice geometry that appears when you go from 1 particle to 2 particle and so on. I don't know that that has worked out. I mean, I think that that's been good for understanding lots of other properties. I don't know that it has yet been as powerful for kind of understanding whether topological invariants apply in the many-body cases, just going sort of directly to n-body.
Sure. Hi, Joel. Hello. So just one question regarding this transmission, this thing through graphene, So this quantization, I mean, how stable is it to, addition of disorder and also interaction strength? And particularly if I go into the puddle region in graphene, in a realistic sample, does it hold or?
No, it's basically, it also doesn't hold at high frequency. It holds in an intermediate range of frequencies, which happens to be the ones where our eye works. So it's good that way. So basically, the idea is that I mentioned that one is not very topological or quantized because, yes, if you went to the DC limit, it won't work because, as we know, it's hard to see the universal conductivity in the DC limit because of puddles and things like that. And we also know it's really dependent on the linear E versus K relationship of graphene. So if you wanted to kind of draw a picture for it, if I draw something like that, this is how we idealize graphene. But in practice, I should really think about, first of all, these curve. Like if we tried to do it in the X-ray, it wouldn't work because I'd be well above the curvature. And down here, we shouldn't really think about K as well defined because disorder is important. So I would say, I believe that it's ordinarily, unstable at low and high frequency, but our visible is in the range where things are good. And interactions, it was a surprise that it took a lot of people like Georg Schmalian and other serious calculations to work out. Because yeah, if you do the calculation and you don't include all the terms just right, you get a large interaction correction. But if you include all the terms just right, you get that 19 minus 6 pi, and the number is just unexpectedly small. But yes, there are papers by different groups, and eventually people, I think, have converged that that is the right answer. Thank you.